So let's take a look at how the energy piece is going to go into the stoichiometry component of this. So we start with our reference point here as being that final reaction where we take the sulfuric acid, dump it in, we neutralize the potassium hydroxide, and the beaker got very, very warm when we were making our alum. The reason the beaker got warm is that energy was a product of this reaction, which means that thermal energy is leaving the system as the reaction takes place, and it's going to heat up. We call the reaction exothermic because energy is exiting the reaction and going out into the world, causing things around it, like the beaker or your hands, to heat up. We can rewrite this showing energy as being negative. So if energy is over here as a product, the delta H, which is something called the reaction enthalpy, and I don't know why they use H, but delta H here is negative 112 kilojoules, basically saying that every time this reaction happens, this reaction being the reaction of 1 mole of sulfuric acid and 2 moles of potassium hydroxide, 112 kilojoules leave the system. When you think about energy, it works like banking and like your checking account. When stuff leaves, you use a negative sign, and when stuff enters or stuff comes in, you use a positive sign. So the negative says energy is leaving. The opposite of this is a reaction where energy goes into the reaction. Something like the cold pack, where energy is a reactant. If you put the cold pack on your hand, that 25 kilojoules of energy comes from your hand, leaving your hand colder than what it was before. And that's called an endothermic reaction. Its delta H values are positive because energy is entering the reaction. So we basically have two kinds of reactions. We have an exothermic reaction where the energy flow is out of the reaction. So just like your checkbook, when money flows out, it's negative. Energy is a product of the reaction, and an exothermic reaction feels warm or hot. Whereas an endothermic reaction, the energy flows into the reaction. It's got a positive sign, because when money's flowing into your checking account, you use a positive sign. Energy is a reactant, and because energy is flowing into the reaction, it's leaving someplace else, like your hand, and if you touch it, the reaction's going to feel cold. From here, we can start to do some calculations with the stoichiometry component of this and use a lot of the same ideas that we've used in the past. So we're going to start with methanol. Methanol is a fuel, or methanol is used as a fuel in high-performance race car engines. It's another petroleum product. Just like gasoline, it's just a very small molecule, burns very clean, very efficiently, and very fast. And in a race car, fast is what we're looking for. So the first question is whether it's endothermic or exothermic. To answer that question, we just have to look at the sign right there. That's a negative sign. Negative means dollars are leaving. Money is exiting your checkbook, exothermic. Not surprising, because race cars burn up energy and engines get very, very hot. If we want to do stoichiometry with this, we are going to rewrite the equation and we're going to put this where it belongs. If energy is exiting the system or exiting the reaction, that means it's getting made as a product of the whole thing. So we're going to rewrite this thing, putting our energy in where it belongs. If this is exothermic, you put the energy as a product. If this is positive, it means energy is flowing in. We'd put it over here as a reactant. So preparing for stoichiometry, 2CH3OH, which is a liquid, 3O2 gas, makes 2 CO2, plus 4 H2O, plus the appropriate amount of energy, 1,282 kilojoules. So all I did was I moved the energy that's exiting the reaction over onto the product side because it's a product of the reaction. And now the question says, calculate the amount of energy released when 1 gallon, or 2.99 kilograms of methanol, is combusted in a race car engine. So we're going to be trying to create a comparison between methanol and energy. And this is really nothing more than a dimensional analysis problem. We just need to understand that this 2C3OH is actually 2 moles of CH3OH producing 1,282 kilojoules worth of energy. And then we're just going to set it up as a dimensional analysis problem. We want to know how much energy, which is really just how many kilojoules, is released when 2.99 kilograms of methanol is burned. Things that I know. The most important idea of the day is that I can look at this balanced chemical equation and know that 2 moles of CH3OH will produce 1,282 kilojoules of energy. And the 2 right here is the same 2 that's in the balanced chemical equation. Be sure to look at the balanced chemical equation to find out how many moles it takes to produce that much energy. Well, that means I'm going to need some other things here. I'm given this mass in kilograms, but I'm given my energy relationship in moles. So I'm going to have to get from kilograms to moles somehow, getting myself probably to grams first. There are 1,000 grams in a kilogram. And I need to know how much 1 mole of CH3OH weighs. All right, that's a periodic table question. So find your periodic table, find a calculator. We need a molar mass. All right, in all honesty, most of you probably didn't need that periodic table because most of you know carbon, hydrogen, and oxygen by heart. That's awesome. 32.042 if I've done my math right. What do we think? Yes. All right, I added well. So my plan here is to take my kilograms of methanol, turn that into grams, turn that into moles, and use the fact that 2 moles of methanol gives off 1,282 kilojoules to hop myself to energy. Okay, so let's do exactly what I said. I've got my 2.99 kilograms. Kilogram is 1,000 grams. Then I need to go, so that takes care of that. Grams to moles. 32.042 grams. 1 mole CH3OH. And here's the important part. Got to get that 2 in there because of the 2 in the balanced chemical equation. 2 moles CH3OH. Burning gives off 1,282 kilojoules. And now I just got to do my math. Let's see, we have 3 significant figures there, an unlimited quantity there, 5 here, and 4 here. We're going to be stuck with 3 significant figures in our answer. 5,000, 5, 9, 8, placeholders, 59,800, I believe, if I have run my calculator operation properly. So the beauty of it is that we have only actually added one brand new idea. And that is looking at the chemical equation and finding an energy equivalent. We know how to do dimensional analysis. We know how to manage molar masses. So we really just have a dimensional analysis problem. That's the mathematical end of this. From a more conceptual standpoint, we do need to kind of talk about where does the reaction enthalpy come from. And we're going to use our model kits to help us out. Right, so send somebody from your table over to get a model kit if you're far enough away that I can't hand you this.
Miss Turner?
Yeah.
It's made up.
Okay, so we are going to start by building the pieces of this reaction with our model kits. So I want you and your table there to build 2 of the CH3OHs and 3 of the O2s. Oh, what colors are what? Black is carbon. Looking for my markers here. Oh, they're here. No. Carbon is black. Oxygen is red. Hydrogen is white. There's a methanol. Okay, so here's my second methanol. These little guys, I think, look like 3-legged ostriches if you stand them up. Okay, and remember your oxygen from when we did Lewis structures is a double bonded creature. So my oxygens have to look like this. Here, I need another red. Need 2 more reds? Maybe my kid had one that yours was supposed to have, because I had one more than what I needed. Okay, so in order for this reaction to happen, we have to rip apart the ostriches, rip apart the oxygens, and put the pieces back together to make carbon dioxide and water. So that's what we're going to do. Now, the next part is very, very important. We have to make the noises when we do this. Okay? Breaking bonds takes energy. Okay? So, if we want to take these apart, we have to exert energy to take them apart. So as we do it, we're going to list the type of bonds broken. So first, I'm going to detach the beak from the ostrich. Okay, so grab an ostrich beak, and you have to make the noise. Ready? Okay, do it. Good. Okay, now let's take the beak off the other ostrich. Ready? I'm not hearing the noises. Okay, so bonds broken. So far, we have broken 2 oxygen to hydrogen bonds. Okay, now we need to pull the heads off the ostriches. So that's an oxygen to carbon bond. Rip the head off, make the noise. Okay. So now we broke 2 carbon to oxygen bonds. Okay. Now we got to get the feet off. How many broken bonds is that going to be? 6. 6 carbon hydrogen bonds. All right, rip the feet off. Got to make the noise. Getting quite the mess here. So that was 6 carbon hydrogen bonds, and now things are starting to roll around because they're unhooked. And now we still have to tear these things apart. How many oxygen to oxygen double bonds do we have to tear apart? Oh, we get to count it as a double bond though. 3. So we get to rip apart 3 oxygen to oxygen double bonds. Okay, make the noise. Now we're exhausted because we put all this energy into breaking the bonds. Okay, now we just have to figure out how much energy that was. On your green resource sheet that I gave you last time, there is a bond energy chart. Things are going everywhere.
I need one more for Kinsey.
Okay. So our resource sheet has some bond energies on it. And those bond energies are also listed in today's little packet. But we're going to use them off the resource sheet. This tells us how much each cost us. So if we look down the list here, oh no, my pieces are rolling away. We need to figure out what did it cost to break a hydrogen-oxygen bond. So hydrogen-oxygen bond, right there. Okay, it costs 464 kilojoules to break 1 mole of OH bonds. Okay? Well, our simulated pulling apart of the model kit represented not just 2 bonds broken, but 2 moles of those bonds broken times 464 kilojoules per mole. So the removal of the beaks from the ostriches cost us we had to invest 928 kilojoules to remove the beaks from the ostriches. Then we removed the heads. We broke a carbon-oxygen bond. So we have to go back to our chart and find carbon-oxygen. Okay, right there, carbon to oxygen single bond, 360. So 2 moles of carbon-oxygen single bond. $720 kilojoules to remove the heads. Then we had to take off all the feet. That was a carbon-hydrogen bond. We had 6 feet to remove. Let's see, that's a carbon-hydrogen bond. That costs 414 kilojoules per mole. That was expensive. 2,484 kilojoules. And 3 moles of oxygen to oxygen double bonds. So that on my chart, oh, that's way over here. Oxygen to oxygen double bond. So that costs 498 kilojoules per mole. So altogether, the energy we invested in destroying all of those bonds is going to be the sum total of the amount of energy it took to do each step of the process. So we spent 928 kilojoules taking the beaks off, plus 720 removing the heads, plus 2,484 to get the feet off, plus 1,494 to break up the oxygens. So all of that cost us 5,626 kilojoules worth of energy. That's energy flowing in. Okay. We had to put it in. So that's a positive number. But the reaction's only half done. We broke it into all these pieces, but now we have to make the things that are the products. Okay, so we need to make some carbon dioxides. Remember from doing Lewis structures that carbon dioxides have oxygen to oxygen or oxygen to carbon double bonds. So, okay, now here's the new sound effect. It's energy coming back out again because the bond is so relieved that it got to be formed that it let out a sigh of energy. Okay. That sound reminds you that the energy is coming back out. So you need to make the sound of the energy coming back out again. And you might have to use some springs from your box because the type of bond doesn't always remain the same. Ah. Need to get some more springs. Ah. Then we need 4 water molecules. Ah. 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 Okay, so all of those pieces got put back together, releasing energy every time we formed a bond. So we need to now just count how many new bonds we formed. We made 1, 2, 3, 4 carbon to oxygen double bonds. So 4 carbon to oxygen double bonds. And 1, 2, 3, 4, 5, 6, 7, 8 hydrogen to oxygen single bonds. Now, the only thing we have to be a little bit careful of here is that the double bond in carbon dioxide, the carbon to oxygen double bond, is a really, really stable bond. So it is a different bond energy than your average carbon to oxygen bond. You may have noticed in the process of writing chemical reactions that we make carbon dioxide all the time. And it's because that carbon to oxygen bond in carbon dioxide is very, very energetically favorable that happens. And so most carbon to oxygen double bonds only involve 736 kilojoules of energy, but the carbon to carbon in carbon dioxide is 799. So we have 4 moles, I'm going to hit the edge of my paper here, times 799 kilojoules per mole. Four times 799. Big old sigh of relief. 3196 kilojoules. And then 8 of the oxygen hydrogens. So that's this one up here, 464. So that's 8 moles. Hydrogen oxygen is 464 kilojoules per mole. So add that whole mess up. But when I sighed, was that energy going in or energy coming out? Energy coming out. So the sum total for the whole entire thing is just to add these two pieces together. I put 5,626 kilojoules in. That's positive. I add that to the negative 6,908 kilojoules right there. And would you look at that? When I add the two pieces together, add the positive number and the negative number together. Negative 1,282 kilojoules. Huh. That number looks familiar. There it is. The amount of energy absorbed or released by a reaction has to do with the energy spent or going in to break the bonds compared to the amount of energy released or coming out as the new bonds form. And so if you take a tally of all the different bonds in there, you can figure out how much energy is either going in or going out in the whole process. Those are the two big new ideas for the day. Here's some definitions. Bond energy is the amount of energy required to break a chemical bond. We did it as positive if the bond breaks, negative if the bond forms. That's just another copy of the bond energy chart. So I'm going to get you started on this next problem and then let you work your way through to make sure you've got the hang of it. We are not going to try to build this one. I'm not going to make you build 25 O2s. However, in order to do these problems, you do have to redraw the reaction in Lewis structure form, because we have to count how many of these different bonds we make and break. So we're going to have it in Lewis structure form. So here we have a C8H18. That's an octane. We've now spent a little bit of time playing with these carbon compounds. 1, 2, 3, 4, 5, 6, 7, 8, and then 18 hydrogens. So there's that thing. Times 2. I vote not to draw a second one. Oxygen is like that, times 25. I vote not to draw 25. Produces some carbon dioxide. Times 16. Plus some water molecules. Times 18. And from there, I would like you in your table to calculate the energy invested in breaking bonds, released in forming new bonds, get yourself a delta H value, and use that delta H value to do the calculation for the amount of energy released when 1 gallon of octane is combusted in your car engine. I just counted them. I broke 1, 2, 3, 4, 5, 6. Because I had to do it for 2 molecules worth. I broke 7 carbon to carbon bonds to break apart 1 molecule, but then there was a second molecule. So I had to break 7 bonds twice, which is 14. I don't know. Did I read the chart wrong? Oh, I did. How about 414? That's our delta H value. Yep, so once we've done all this bond energy nonsense, we now know that the delta H is negative 10,060 kilojoules. So now we're on to doing the stoichiometry part of this. Because it's leaving the system, it's a product. So we just tack it right into the chemical equation. And now we can do what we did before, and you can calculate how much energy is released when you burn a gallon of gasoline in your car. going to take a field trip.
No way.
Okay. There we go. That's all there is to the thermochemical stoichiometry. You really have to have essentially 3 skills coming out of today. Number 1, look at the delta H value and or the chemical reaction to declare is this endothermic or exothermic, and then accordingly will it feel hot or feel cold. Number 2, if you have the chemical equation, figure out how much energy is going to be released from a given amount of something being reacted. And skill number 3, if you're given the reaction and that bond energy table, to be able to use the bond energies to calculate the delta H value. Don't try to skip the step of redrawing it with Lewis structures, because that will cause you to accidentally either pick the wrong number of bonds or it will cause you to pick the wrong kind of bond. So you might overlook the fact that this is a double bond and you might calculate just an oxygen-oxygen bond if you don't try to redraw the Lewis structures. Or people very often look at this and go, well, there's 8 carbons, so I got to break 8 carbon-to-carbon bonds. But you don't really. If you have 8 carbons connected together, you only have to chop 7 bonds to get the carbons chopped apart from one another. So drawing these pictures will help avoid making silly mistakes. So at this point, if you don't need to see any of these problems that I'm about to work, you are free to start working on your homework. We are going to have a quiz next time that will pick up the gases and solution stoichiometry. So this one is solutions, this one's gases. And then your homework is the book sections and practice problems for section 3 or for learning target 3.5. Next time on Wednesday, we'll take your quiz and have kind of a wrap-up day, and then your test is going to be on Friday. So at this point, if you don't need help with any of these problems that we listed on the board, I am not offended if you start working on your homework. That really makes sense to get the best use of time, and I'm going to start working through those problems.